Okay, sorry for the delay. Here we go. So we're going to finish up chapter 12 here. Hopefully should be a shorter class today. So we want to use chi-square. We did the goodness of fit test. And what were we doing? We were looking at a certain distribution of a variable and comparing it to an expected distribution of that variable, right? And we're using the chi-square test to say, hey, this distribution is not exactly what we expected, right? It's changed from the expected distribution with some degree of certainty. Okay, so the chi-square, this goodness of fit test, can also be used for the idea of checking for independence of two variables, right? So independence is about two variables. So again, before the goodness of fit we've done was just looking at one variable, comparing it to what we expected for the distribution. So independence test is comparing two variables. And so what does it mean that two variables are independent if the outcome of one, or another way they put this is not associated. So two different ways to communicate, to kind of, you could say they're independent or they're not associated if the outcome of one does not influence the outcome of the other. Okay, so for instance, if I asked you all your favorite color, and we looked at that as one variable, and then I asked you all how long it takes you to get to campus, would these be independent or dependent variables? Would knowing your favorite color have some influence on your travel time to campus? No, this is an example of independent variables. Okay, and then if I said we were going to look at the temperature outside and the number of people at Tempe Town Lake, would these be independent or not independent variables? Influence? If we knew the temperature outside, would that influence how many people would be out at Tempe Town Lake? Yeah, if it's 119 in the summer, right, there are less people at the lake. And if it's 74 degrees outside, then there are more people at the lake. So that's the idea of independence versus dependence, and we can use the chi-square test to look at two variables and say, hey, this one, the outcome of this one is actually influencing the outcome of the other, or there's not enough evidence to suggest that. Okay? So that's the idea of independence. And so we just have to kind of frame it, and then it's the same old goodness of fit test that we had before. Any questions on that? Okay, so here's what's called a contingency table. So we have this table where they surveyed 1,772 people. That's the total number of people. And then they broke it down by two variables, marital status and how many drinks per month. And they want to ask the question, does marital status have a effect, a influence on how many drinks per month you have? So by kind of working on these numbers here, all this raw data here, we can kind of answer that question. At some level of significance, can we say that yes, marital status has an influence on drinks per month? So I'm actually we're gonna work on it in a second, but let's. Okay, made it. All right. So here's what we're going to do. Here's the hypothesis test we're going to have. Oh, first of all, so you have some setup here. You have that all expected frequencies are 1 or greater. And at most 20% or less than 5. And I think that's the same thing we had for what we did before, the goodness of fit. You have a simple random sample. Here's our null and alternative hypotheses. The two values are not associated. Another way to say that does it mean independent or not independent? Not associated. Independent or not independent? Independent. So there's another way to say that. Okay? The alternative is the variables are associated. Okay? Some degree of dependence. Okay? And so like before, we're going to have a significance level, and we're going to use our goodness of fit test to come up with a chi-square test statistic. Okay, so and then we're gonna find the critical value based on the significance level and degrees of freedom, and we're gonna, just like before, we're gonna compare our test statistic to the critical value, and then we're gonna either reject or not reject the null hypothesis. Okay, are we good for this? Let's go. We can go back to our example if we're good. Okay, so here were some of these are observed. Also, all these in the box. These are observed frequencies. So, for instance, there are 411 married people in this out of the 1772 that abstained altogether from drinking. Okay, 7 widowed people over 60, or seven widowed people had over 60 drinks per month. Okay, so these are the observed, and so what we need now is the expected. So when we're finding the expected, it's what would be expected if they were not associated. Okay, what would we expect for single people that abstained if these two variables were not associated or they were independent? Okay, so how we find that out is according to the survey, we find what percent of people abstained, first of all. So how would you find the total percent of people that abstained from drinking altogether? What would you do? So how would you calculate the percentage or the portion of people that abstain from drinking? Let's see. Michael, what do you think?
You would take the total number that abstained and divide it by the total number of people that you surveyed.
Which is, so what would it be?
So just for singles or for everybody?
The total number of people who abstain from drinking.
590 divided by 1772.
That's right. So 590 over 1772. Okay, so let's just get that out there and get a number for that. Who's got it? 0.333. Agree with that? Someone else get that too? Okay. So that's like a third. So if the marital status has no bearing on drinks per month, and we have 354 single people, then what would we expect if these are independent? How many of these 354 would we expect abstain? How would you find it? What would you do? Or in general, what would it be? So we've got 354 total single people, and we're assuming that marital status and drinks per month are not associated, they're not dependent. So how would you calculate how many single people you would expect to abstain? Yeah. So we're going to take 33% of 354. That's what we would expect if there's no influence on the two. And then how many married people would we expect to abstain from drinking? If there's no correlation between, or no association between drinks per month and marital status, what would you do? Whitney?
Take the total amount of married multiply and multiply that by
Total amount of married.
and we take that and which just saying find the percent.
So we found that 33% of all people abstain. And so if it doesn't matter what their marital status is, and we have 1,173 married people, how many would you expect abstain? Or how would you get it?
1,000.
Again, 33% of that, and then you take 33% of 143, that's what we would expect for widowed. And then 33% of 102, and that's what we expect for divorced. Okay? So, everybody you pick two. From each column, pick two values, so two abstain, 2, 1 through 60, and 2 over 60, and find the expected number of people that would fit in that category if these weren't associated. Okay? Does it make sense? Can you do it? So everyone pick two. Don't pick the first two. Everyone pick a different number of two. Okay, so 2 of those, 2 of those, 2 of those, and find how many you would expect to fit in that category if marital status was not associated with drinks per month. Work together. See if you can do it. Hey, compare with someone around you, see how you're doing. Does anybody want a chi-squared table after this amount? That's top to the back. Good enough, everybody? Okay, so see how you did. Did you get the ones that you picked? Did you get them right? Some are nodding. Yes? Any questions on this? So now what are we looking at then? So we've got the observed. We got the observed data, which is the first number in each box. And then we have what would we expect if there was no correlation, no association between these two variables in the second in each box. So observed and expected, right? Just like before. So now we have for each of these 12 categories, we have an observed and expected. And so we're going to use the chi-square test to see if how the chi-square statistic is going to be a measure of how different those are, how different the observed is from the expected. The more different those are, the more likely that we have a dependence between marital status and drinks per month, that one influences the other. The closer these are together, the lower the chi-square statistic is going to be, and then the less likely it is that these have a association or a dependence to them. Okay, doesn't make sense. Okay, so then the degrees of freedom. You're going to take the number of outcomes of the one variable, say rows, minus 1 times the number of outcomes in the other variable, minus 1, and multiply. So we have 4 rows, 4 different outcomes for marital status. So we're going to take 3, 1 less, times, and what do we have? We have 3 different categories for drinks per month. So we're going to take that minus 1, so times 2. So we're going to use 6 degrees of freedom when we get our critical value from the chi-square test. Okay, so in StatCrunch, so if we were going to do we've got what, 12 different observed and expected. We'd have to make a table that had 12 rows in it. Find each observed minus expected squared divided by E and sum all those up. Okay, so we did that one time last week. That would, for 12 different things, that'd be a lot of work by hand. So as we know, we're going to take advantage of StatCrunch. And so I've got them in there. This is the same data, right? Is that the same? Those the same numbers? Okay, good. So what we're going to do is we're going to go to, so this is going to find our chi-square statistic, which is the observed minus expected squared divided by expected, and then we're going to sum all those up. In this case, we're going to have 12 things to sum up, and that'll get us the chi-squared number. The further that observed, so since it's, since each one is O minus E squared over E, and we're summing that up. So the further apart that each observed is from the expected, when you're going to get a bigger number here, and you're going to sum together, and then the bigger those numbers are that sum together, the bigger your chi-square statistic is going to be. And the bigger that number is, as we know, the more and more likely observed is different than expected. And we made our expected based on that they're totally independent. So the further away the observed is from expected, the more dependency we're seeing, and the less independence. Okay, so here's how you do it. You're going to go stat, tables. Okay, so stat, tables, contingency. So contingent, we're seeing if one variable is contingent on the other. Okay, table, contingency, and then with summary. All right, so now we got to select the columns that have data in them. So our columns with data are 2 through 4. Variable 2 through 4. So select those 3 columns. And then for the row labels, we're going to tell it that the variable 1 column here has the labels for the rows. Okay? And then we're going to do, so if we want, we can do this expected count for us. We can display expected counts. Those are the ones we just calculated. And then we want the chi-square test for independence. All right, and so we can compute. And these, again, the numbers in parentheses would be what would we expect if they weren't associated, right? If they weren't associated, what would we expect? And so what's our chi-squared value? 94.27. 6 degrees of freedom, which we calculated. Okay, so our test statistic is, we got chi-square is 94.27. We have degrees of freedom. Okay, so we got that. And now for our critical value, degrees of freedom is 6. And let's do a significance level of 5%. Pretty standard. You got your chart. What do we got? $12.59? That's what I'm seeing. So chi-squared alpha, that's our critical value. I'm reading it as 12.59. You agree? Okay, let's make a picture. Let's remember our chi-square statistic. Left skewed or right skewed? Right skewed. Okay, and so our critical value, 12.59. So, is this number suggesting that the numbers are significantly different and we should reject the null hypothesis? Or is this number suggesting that we don't have evidence, there's no evidence to suggest that those numbers are different enough at the 5% significance level? So are the numbers different or not? Okay, so high chi-squared means there's a cumulative effect that these are very different from each other, observed and expected, right? Observed minus expected is summing up cumulatively to be a very high number, meaning these are quite different. And our expected was, we were saying we expect them to be not dependent. We made all those calculations based on if this had no bearing on number of drinks per month. Therefore, here we are, way out here. So our null hypothesis was that they're independent or not associated. We're going to reject or not reject the null hypothesis. Okay? Without hesitancy, we're going to reject, right? This is way bigger than 12. Because that's way bigger than 12. These values cumulatively are very different. So what's our conclusion? There is great evidence to suggest that marital status has a strong effect on drinks per month. Okay? So we're rejecting the null or the alternative, which is these are dependent variables. These are dependent variables. Okay, does it make sense? Any questions on that? What's that? Oh, you didn't get it right. So what did we say? We said that 590 over, so the number of who abstain, what was that total? 590? So do you understand that 590 over 772, that was 33%? Or 1/3. So if there was no dependency on marital status, then we would expect 33% of singles to abstain, 33% of marrieds to abstain, 33% of widows to abstain, and 33% of divorced people to abstain, right? If there was, then we'd expect, like here it's what was it showing? Way more married people are abstaining than 33%, and less than 30%, way less than 33% of divorced people are abstaining. Okay, so we just need to take 33% of each of those, and then when we get to 1 through 60, so 1 to 60 drinks per month is going to be 957 over 1772. Did you get a number for that? 0.5 what? Or 6? Five? One more variable. 540. Okay. So if then of all the single people, if these weren't correlated, if there was no association between these two, then we'd expect 54% of all the single people, and 54% of all marrieds, and 54% of all widowed, 54% of all divorced, to have 1 to 60 drinks per month.
So you just, when you get that decimal,
Mhm.
you just multiply that by how many did.
So how many total single people do we have?
Um,
354, right? So we want 54% of all the single people. That's what we would expect for single people who take 1 to 60 drinks a month. And then there were 1173 marrieds. We would expect 54% of them to have 1 to 60 drinks per month if there was no association between the two variables. Is it better? Yeah. It's given. So we're going to do a test. So it's always given, right, when you're doing a hypothesis test. Other questions? Okay, so let's look at okay, and then you have the if you want to do the p-value approach also, it's just looking at the exact same thing a different way. You're going to compare the alpha value. You're going to compare your alpha to the p-value that you get from your chi-square test statistic, right? So you have, this is the test statistic. And there's a certain p-value associated with that. Or what was that again? That is the probability of a type 1 error. Probability that we reject, but we wrongly reject. Okay, and so then you just compare the p-value to alpha. If the p-value is less than alpha, you have less area to the right, you reject. If your p-value is greater, as that area is greater than the significance level, then you do not reject. Okay, but it's just two different ways to do the exact same thing. comparing apples to apples over here, your test statistic to your chi-square critical value, or comparing the p-value that you get from the test statistic to the significance level. Comparing areas. So comparing chi-squared values versus comparing areas. We've seen it before. Okay, so let's look at another example. Maybe, do I have the book open still? There's it. You can't have more than one of these things open at once, which is unfortunate. Okay. So one of these I had set up already. Let's see. Okay, I guess it's in. Okay. So we'll just pick one here. Okay, so the original movie reviewers, this may be before your all time, but the original movie reviewers were Siskel and Ebert. Okay? Okay, we're okay. All right, so let's see if this is for, I guess this is for a year's worth of movies or something like this. And this is the summary of the data. Siskel's ratings, thumbs up, mixed and thumbs down. Ebert's ratings. So for each movie that they reviewed together fell in one of these 9 categories. They both gave it thumbs down. One gave it thumbs up, the other gave it thumbs down, etc. Okay? So let's see if Siskel's ratings and Ebert's ratings are, is there some association between those, or are they independent? Okay? Are they? And so we'll do that at the 1% significant level. So they want the 1% significance level. Okay, and so we're not going to do it by hand here. So our first column, we can do thumbs down, mixed, thumbs up, and then thumbs down. Okay, and we can put the numbers in. So 24, 8, 10, 8, 13, 9, 13, 11, 64. when you're doing the homework, there'll be a little icon that you can click, and it should bring up the data in the particular problem, just like this. Okay, so you don't have to type it in like that. You should, if you click the little teeny icon for the stat crunch, it should bring it up like this. Okay, so let's review it again. You can do stat, tables, okay, contingency with summary. Okay, stat, tables, contingency with summary. And what do we want? We want 2 through 4 again. And then the labels for the rows was in the first column. We can show expected counts, that's optional. And then chi-squared test for independence. Okay, this is for your green sheet. So you're going to finish the problem now. So at a 1% significance level, we're asking so you need to write out your null and alternative hypothesis. Your significance level is 1%, and you're going to do the test. So and then write out a statement of conclusion. Okay. So I'll put that over here. Okay, so 4 parts to this. You're going to write the null and alternative hypothesis, execute the test, then are you going to reject or not, and then you're going to explain that conclusion in a sentence. Okay, 1 more minute, and we'll do a new one. Okay, we're going to go on to another example here, this one here. Okay, so this was depression and bone mineral density. So they looked at a sample of almost 2,000 elderly Asian men, and they were looking at if they were depressed or not, and then their bone density, and they were trying to see does depression have effect on this physical attribute in your body of your bone density? Okay, so let's put the data in here, and so let's check this at the 0.5% significance level. We're going to do a test at the 0.5% significance level. So I guess does anyone know what osteoporotic means? Does that mean like super low density? I'm guessing. And then just low. And then normal. And then depressed and not depressed. Okay, so I'll show you one more time here. So when you hit the numbers for Siskel and Ebert in there, if you notice that you didn't say anything, shame on you. Okay, stat, tables, contingency, with summary. Okay, try again. When you're done, you can go. You can turn it in and go if you're satisfied, or I come around for questions. 0.5% significance. You have to figure out the